Hello everyone, my name is Yashant Taliwal and I am a third year BSc Bioveterinary Science student at Dalhousie Agricultural Campus. Today I am going to present my research project that I completed this summer. I worked for the project named Bimodal Data Analysis for early detection of lameness in dairy cows using artificial intelligence. Henching by a master's student from the University of Waterloo also helped and contributed in this project. I completed this project under the supervision of Dr. Suresh Nithirajan, an associate professor at the Faculty of Computer Science and at the Faculty of Agriculture at Dalhousie University. Now moving on to our presentation. Firstly, I would like to present the graphical abstract of our research project that visually represents the major key points of our research project. As you can see in the picture, there is a cow standing with arched back, joint flexion, asymmetric steps, and other limb issues, showing the signs of lameness. So lameness is a painful condition in dairy cows that significantly impacts both their welfare and economic productivity. As one of the most economically significant health issues in Canadian dairy herds, early detection is crucial to minimize welfare concerns and financial losses. Our study employs a bimodal artificial intelligence approach, integrating facial biometric data collected using smartphone and accelerometer-based movement data collected using Fibion sense motion sensors to detect early signs of lameness. Data were collected from 6 Holstein cows over a period of 21 days, capturing variations in facial expressions and locomotion patterns. A multi-model AI model was developed by combining DenseNet for image analysis and long short-term memory networks for time series accelerometer data. By using AI and this model, we were able to detect signs of lameness in dairy cattle very quickly and accurately, improving animal welfare and reducing economic losses. So now, what is lameness and how does it affect cows and farmers? Lameness is a clinical disorder impairing locomotor system and adversely affecting cow posture, movement, and overall locomotion. It is a significant health and welfare challenge in Canada and globally. This condition causes pain and discomfort, reduces longevity, milk production, and compromises fertility. It also imposes substantial economic losses on farmers by increasing handling expenses related to medical care and treatment, in addition to the premature culling of the animals, and thereby diminishing the overall welfare of dairy cows. More than 1,500 articles on lameness in dairy cows have been published since 1990, thereby underlying the significance of this condition. In the right, you can see a picture of a cow showing the signs of lameness like arched back, joint flexion, asymmetric steps, and reduced walking speed. Now we will talk about conventional methods for detection of lameness in dairy cows. The conventional method for assessing lameness involves observing a cow's walking gait using various scoring systems called lameness scoring system. Most widely used lameness scoring system is a 5-point lameness scoring system or Sprecher. An illustration of 5-point Sprecher system is depicted in this slide, as you can see on the right. The system categorizes lameness into 5 distinct stages based on abnormalities in gait, back posture, and standing posture. However, these methods are inconsistent and reliability of the subjective method varies. Moreover, the detection of mild lameness is often delayed by these methods, prolonging the gap between the onset and the treatment. Therefore, there is an increasing shift towards the automated technologies that promise quicker and more accurate lameness identification. Moving on to our next slide. So we're going to talk about the automated lameness detection systems that are more advanced and more reliable than the conventional methods. Automated lameness detection systems mainly utilize 3 approaches: kinematic, kinetic, and indirect approach. These methods involve the use of advanced technologies like pressure sensitive mats, accelerometers, and computer vision system to access gait and behavioral changes indicative of lameness. Despite better results, challenges such as environmental interference, camera placement limitations, and need for extensive image data processing continue to hinder the practical application of these systems. To address these limitations, emerging technologies like biometric facial recognitions are being integrated into the field, offering new avenues for non-invasive, precise identification and monitoring of dairy cows. As you can see in this slide, the first picture shows a cow equipped with the accelerometer sensor. In the second picture, the cows are standing on the pressure sensitive mat. And the third picture represents computer vision system in which a camera is capturing the gait of a cow. As both conventional and automated lameness detection system have some limitations, so therefore there's a need for more advanced and newer technology. So now I'm going to talk about the biometric facial recognition for detection of lameness in dairy cows. The research on cause-specific facial grimace scales for pain or lameness is still developing. While grimace scales have been created for various species, including cattle, their application specifically for lameness detection is not as well established as other methods. Facial expressions should be considered alongside other indicators of lameness, such as gait analysis, posture changes, and behavior alterations. For interpretation of facial expressions, context and individual variation among cows needs to be considered for more accurate results. The WUR Wolf, a real-time facial recognition platform, aims to detect various emotional states in farm animals, including cows, based on facial features, but its specific application to lameness detection is not clearly stated. Automated systems for detecting these facial changes in cows are still being developed and refined. Therefore, for the most reliable lameness detection, it's recommended to combine observation of facial expressions with either other established methods of lameness assessment in dairy cows. Moving to the methodology of our research project, firstly, I would like to speak about animal specifics. Six Holstein cows housed at Ruminant Animal Center of Dalhousie Agricultural Campus in Truro, Nova Scotia, were chosen for data collection. The cows were classified as lame and healthy based on their unique ear tag information and verbal confirmation from the staff of RAC. In the right, you can see a picture of mine during the data collection process at RAC, and below there is a table consisting of information about cows and accelerometer sensors attached to them. Continuing further, I would like to explain the process of biometric facial data collection. I collected facial photos and videos of six Holstein cows from Ruminant Animal Center located at Dalhousie Agricultural Campus in Truro, Nova Scotia. Tri-daily schedule was followed in morning, afternoon, and evening to capture the natural variation in the cow's facial expressions and movements throughout the day. The tri-daily schedule encompassed capturing cow images and videos under various contextual settings, like before and after exercise in morning, before and after feed in noon, and during rest in the evening. The images and videos were captured from both front and side angles respective to cow's face and incorporated detailed facial features of a cow like ear posture, eyelid tightening, eye wide visibility, snout tightening, and overall muzzle appearance. Samsung Galaxy F41 was utilized to capture images and videos of cows. The process of data collection was non-intrusive to the cows and involved capturing facial images and videos at a suitable distance to ensure minimal stress to the cows. A total of 7,000 images and 1,000 videos were collected over a period of 21 days from 6 cows. In the slide, you can see a picture of a data collection process. A data collection process encompassed of collection of facial data and the accelerometer data that can be seen in the picture too. Now we'll talk about the variable accelerometer data collection. Fibion sense motion sensors were attached to 4 Holstein cows housed at rack. The sensor was attached to right hind leg of each cow using Velcro strap and duct tape. The sensor measured physical activity of cow in different contexts, including walking, standing, and lying down. The sensor had capacity to monitor data uninterruptedly for up to 15 weeks. A smartphone application of Sense Motion was used to transfer data from sensor to the database server. SenseMotion online visualization tool was used to access cows' physical data through a browser and provided data for download in Excel, PDF, and Fibion report format. Physical data of 4 cows were continuously measured for 21 days in the study. However, sensor attached to cow 1 got damaged on day 10 of data collection. Therefore, partial physical activity data was collected for cow 1. In the pictures you can see in the first picture there is an accelerometer sensor and a cow equipped with the sensor, and the second picture is of the same data collection process that I explained in my last slide. In this slide I will talk about how data was pre-processed. The original data of the accelerometer data has 12 or 13 accelerations recorded for the x, y, and z axes in 1 second. The accelerometer data was enhanced by sliding interception with 60 seconds as the time window and 1200 seconds as the data length. The first 1199 seconds of the built accelerometer LSTM input data are taken as input, and the last 1 second of data is taken as the predicted value and fed into an LSTM model to train the LSTM model. After training the LSTM model, input accelerometer LSTM input data again into the LSTM model to obtain the last LSTM layer, to obtain the extracted features, and finally get a data with 32 feature values. The images were enhanced by randomly flipping the image horizontally with a probability of 0.5, randomly flipping the image vertically with a probability of 0.5, randomly adjusted the brightness of the image, and randomly adjusting the contrast of the image. In the right of the slide, you can see screenshots of SenseMotion smartphone application depicting information about the sensors attached to the cows. Talking about the model construction, we developed a multi-model AI model that combines time series accelerometer data and visual data to enhance detection accuracy. The model was trained using a DenseNet one-to-one framework for image data and an LSTM for time series data. The DenseNet model, a type of deep learning architecture, helps our system to analyze images more effectively by identifying subtle changes in the facial expressions that are associated with lameness. The LSTM model is used to capture the trend on the time series so as to predict the acceleration data of the cows. The multimodal model was constructed to process two different related data, such as data at the same time, thus improving the performance of the model. Moving to the results and discussions, firstly, I would highlight the different metrics like accuracy, precision, and recalls that are related to the AI models. The accuracy of the test set for deep learning model of accelerometer data and photo data and the single model of DenseNet one-to-one is 96.42 and 97.30% respectively. This indicates that movement of cattle in the lame state is significantly different within 20 minutes, and there are also significant differences in facial features. When the multimodal model was trained with an epoch of 10, the accuracy of the test set was 99.55%. Compared with the single model of accelerometer data and photo data, the accuracy of multimodal model is significantly improved. For precision, the precision of the multimodal model was 100%. The LSTM model using only accelerometer data was 98.26%, and the DenseNet using only image data was 98.43%. When it comes to recall, the multimodal model was 98.82. The LSTM model using only accelerometer data was 96.41, and the DenseNet using only image data was 98.61. What is significance of these measures? The multimodal model has absolute advantages in accuracy, precision, and recall. Although recall is only zero point 0.2 ahead of DenseNet, which uses images. This may be because the data set is unbalanced. Precision measures how many of the cows identified as lame were truly lame, while recall assesses the model's ability to detect all lameness cases. High precision and recall ensure that farmers can trust the system for early intervention. Our multimodal model achieved an accuracy of 99.55%, significantly improving early detection of lameness compared to traditional methods. This enables more timely interventions, reducing economic losses and improving animal welfare. Confusion metrics also indicates reliability and efficacy of multimodal model. As can be seen from the confusion metrics, all the lame were checked out correctly and only three not lame cows were incorrectly predicted to be lame. This shows that the combination of accelerometer data and images can be very effective in distinguishing whether cattle have lameness disease, which can help farmers more quickly detect and treat cattle in time. What was the difference between activity levels of lame versus healthy cows? It is evident from the graphs that healthy cows generally showed higher activity levels across various metrics compared to lame cows. Lame cows showed higher resting times and reduced overall activity during peak hours, indicating discomfort. Metrics such as activity lying, sitting, rest, activity upright walk, and activity steps showed significant differences, with healthy cows generally exhibiting higher activity levels. The activity levels of lame cows, on the other hand, were greater for metrics such as activity upright, sporadic walk, activity steps 2, and activity step 6. The lame cows may have exhibited increased level activity levels for these metrics in order to compensate for the discomfort and pain that is induced by lameness. The presence of lameness is not the only condition that might influence activity. Clinical mastitis, for example, can lead to an increase in activity. While lame cows had higher activity for some metrics. It is apparent from the graph that lame cows had higher mean values for metrics like activity lying, sitting, rest time, activity intensity count, and activity step count as compared to healthy cows. However, contrary to activity intensity count and activity step count, activity lying, sitting, rest time was substantially higher in lame cows than in healthy cows. It can be inferred that lame cows generally tend to lay for longer and had prolonged lying bouts. The mean resting time in lame cows suggests a behavioral adaptation to mitigate pain, with increased lying times representing an effort to reduce stress on affected limbs. The prolonged resting behavior has been previously linked to discomfort and pain management in lame animals, reinforcing the physiological basis for reduced activity metrics. The integration of facial integration accelerometer data significantly improved the model's accuracy by leveraging both movement and visual cues. The accelerometer provided data on physical activity, while facial analysis captured pain-related expressions, allowing model to generate a comprehensive understanding of lameness and enabling more effective early interventions. What is the relationship between housing and lameness? Apart from physiological factors, housing condition can contribute to worsening of lameness problems in dairy cattle. The cows that were part of our research were kept in a barn with tie stalls, and each stall was bedded with 4 to 6 centimeters of wood shavings. The influence of stall surface on lame cow behavior has been reported. Lame cows tend to spend more time lying down in stalls that offer a more comfortable environment to rest. This underscores the significance of offering a comfortable lying area, particularly for lame cows. In general, constructive stalls compel cows to stand more in the stalls rather than lying down. In healthy cows, lower mean values of metrics such as activity intensity count and activity steps count suggest that they are unable to perform typical locomotor behaviors due to constrictive environment of tie stalls. Therefore, in an effort to promote the welfare of cattle, we propose that tie stall barns should be prohibited on a global scale around the world. how we used Grad-CAM analysis to highlight the facial features that DenseNet model used to classify the cows. From the Grad-CAM analysis images, we can observe that face plays a large weight in the classification task of DenseNet model. The Grad-CAM analysis highlighted that the eye and the ear regions showed increased tension, which aligns with the known pain indicators such as orbital tightening and ear positioning. These visual cues provide a clear connection between the model output and recognized physiological symptom, enhancing interpretability and confidence in the model's predictive capabilities. What are facial indicators of pain in cows? Similar to humans, animals exhibit specific facial cues when experiencing discomfort or pain. The concept of Grimace scales has been introduced in animal welfare studies to quantify pain through facial expressions. These Grimace scales typically focus on features like tension in the neck, shape of the eye, tension in the brow, nose branching, and positioning of the ears. In dairy cow, notable facial indicators of pain include squinting or tightening around eyes, ears held back or drooping, tightening of the muzzle, and changes in nostril shape. For cattle specifically, studies have looked at facial expressions as potential indicators of pain and discomfort, which could be associated with lameness. During data collection, we observed noticeable differences in the facial expressions between lame and healthy cow. As you can see from the picture in the right, lame cow on the left is showing evident facial tension, while healthy cow on the right is with the relaxed facial features. What is relationship between facial expressions and lameness? Specific facial expressions cannot be correlated with particular types of lameness. So far, facial expressions are looked as general indicators of pain and discomfort rather than diagnostic tools for specific lameness conditions. Facial expression scoring is in cattle is still an emerging area of research. While it shows promise as a potential non-invasive way to assess pain and discomfort, more validation is needed, particularly for its use in detecting or differentiating different types of lameness. In the right, you can see a table showing different facial expression units and expressions that are indicative of lameness in dairy cattle. What is novelty of a research? The limitations of current automatic lameness detection system include system costs, detection ability, positioning requirement, low efficacy, and installation in practical application systems. This study differs from prior research by integrating both visual and accelerometer data, which has not been explored extensively in the context of early lameness detection. The combination of facial recognition and movement data offers a more comprehensive understanding of early indicators of lameness. Major focus of our AI model is predicting lameness even before it happens, and it can help to predict lameness possibly 4 to 6 weeks in advance. Furthermore, our model has an advantage over the current automated lameness detection systems in terms of integration into the commercial dairy farms. Our system could be deployed via simple smartphone application connected to accelerometer sensors, allowing farmers to monitor cow health in real time. On the right, you can see first image. It's a screenshot of Sense Motion smartphone application. And the second image, it's a screenshot of Sense Motion online visualization tool. What are limitations of our research? As AI system becomes increasingly integrated into the livestock management, it is essential to consider the issues of data privacy, farmer autonomy, and transparency of AI-driven decisions. To tackle these ethical issues, precise rules and regulations regarding the usage and prevention of data are necessary. Environmental situations like variability in lighting, diverse weather conditions like rain, fog, or snow, physical barriers in farm environment have a substantial impact on accuracy of facial recognition technology in dairy production. Moreover, effective application of this technology in dairy farming is further hampered by software constraints, the need for constant internet connectivity, and the expense of setup and maintenance. A limitation of our study is the relatively small sample size, which may not fully capture the diversity of dairy cow behavior across different environments. Hence, The broad adoption of this integrated approach of lameness detection will require the development of more affordable solution along with advancements in the both hardware and software to overcome these obstacles. Concluding my presentation, I would like to mention few key points from our research and where do we go from here. The multimodal model established in this study, which combines accelerometer data with photos of cattle, has potential to be very efficient in identifying whether or not cattle have lameness disease. This can assist farmers in detecting and treating lameness in cattle in a more timely manner. With the help of a system, farmers would be able to track health of their cows in real time by connecting accelerometer sensors to the straightforward smartphone applications. In addition, the advanced technology of AI, which includes deep learning and convolutional neural networks, can also assist in the effective comprehension of behavioral distinction between the lame and non-lame cows. AI's ability to improve health management and well-being is significant since it enables early disease detection and stress recognition, resulting in enhanced care. Future work will focus on scaling this approach to commercial dairy farms and further refining the AI model. At the last, I would like to acknowledge our funding sources that funded our research project and the management and staff members of RAC that help us in the process of data collection. Thank you.